Welcome to Deep Dive with Emily and Phil. Today, we're taking a deep dive into the world of probability.
Oh, fun.
You've sent us some lecture notes on probability concepts and notations. It looks like they're part of a larger data science series.
That's right.
Yeah.
Probability is fascinating because it's woven into our lives, influencing our decisions even when we don't realize it.
Right.
These lecture notes lay the groundwork for understanding how data scientists grapple with uncertainty and make predictions.
It seems like one of the first things these notes address is how symbols can have different meanings in probability versus linear algebra. I've got to admit, seeing X used in different ways can be a bit confusing.
Definitely. It's like learning a new language.
Right.
The lecture notes highlight this right away.
Okay.
In linear algebra, a lowercase x often represents a vector or a variable, and a capital X usually stands for a matrix. But in probability and statistics, they mean something completely different.
So what does X mean in probability then?
Well, a lowercase x refers to an event that's already happened in the past.
Okay.
Think of it as a known outcome.
Got it.
On the other hand, a capital X represents a random event that could have multiple possible outcomes, but we don't know which one will actually happen yet.
Okay, that makes sense.
Yeah.
So the lecture notes jump right into the difference between a probability mass function, or PMF,
Right.
and a probability density function, a PDF. Professor Wu uses rolling a die to explain a PMF.
Right. PMFs are all about discrete events, things you can count, like the possible outcomes of rolling a die, 1, 2, 3, 4, 5, or 6. The PMF tells you the probability of each of those specific outcomes happening.
So if I rolled a die 6 times and got 2 1s, 2 4s, a 3, and a 5, the PMF would reflect that, right?
Exactly.
Yeah.
The PMF would visually represent the likelihood of each outcome based on those rolls.
Got it.
Now, PDFs are different.
Yeah.
They deal with continuous events,
Okay.
things that can take on any value within a range, like time or distance.
The lecture notes use the example of studying time and getting a higher grade. It's not about studying for a specific number of hours, but the probability of getting a certain grade based on how much time you spend studying.
Precisely. PDFs are about finding probabilities within a range,
Got it.
not at a specific point.
Got it.
Imagine a curve that represents the probabilities. To find the probability of an event happening within a certain range, you'd need to calculate the area under that curve.
So that's where calculus comes in, right?
Yes.
I see a Python code example in the notes.
That code shows how to use Python to find the probability of an event falling within a specific range on that continuous curve.
Okay.
It's a powerful tool for working with PDFs.
This is interesting, but things rarely depend on just one factor, right?
Right.
How does probability handle the complexity of multiple things happening at once?
That's where multivariate probability comes in.
Okay.
And the concept of joint distribution. It's basically the probability of multiple events happening together.
So instead of the probability of just rolling a 3,
Yeah.
it could be the probability of rolling a 3A and D, flipping a coin, and getting heads.
Exactly. And the notes show different ways to write it. P of X, comma Y, P of X and Y, or even an intersection symbol. They all mean the same thing. The probability of both X and Y happening.
Okay, that's starting to click.
Good.
Earlier, we talked about PMFs and PDFs using AND logic.
Right.
The notes also mention OR logic, and there's a Venn diagram too.
Right. Or logic in probability is a bit different.
Okay.
Imagine wanting to know the probability of rolling a 3OR, flipping a coin, and getting heads. The Venn diagram visually shows how to calculate that.
So you add the individual probabilities of each event,
Yes.
but then you have to subtract the overlap where both happen to avoid double counting, right?
Yes. That's the key takeaway when dealing with OR, logic, and multiple events in probability.
So we've talked about the probability of 2 events happening together. But what if we want to find the probability of just one event happening? Even if we know the probability of both,
Yeah.
can we extract that information?
Absolutely. That's called marginalization.
Okay.
Think of it like zooming out from the combined probability to focus on the individual probability of one event.
Professor Wu uses a table to illustrate this. So if you have the probabilities for different combinations of events, you can add up the probabilities related to one event,
Right.
ignoring the other,
Yeah.
to get its overall probability.
The table is a great visual for that zooming out process.
Okay, so marginalization is about isolating the probability of one event when you have information about the combined probability of multiple events.
Exactly.
Now I see the lecture notes bring up conditional probability.
Okay.
What is that exactly?
Conditional probability is all about how new information can change the likelihood of something happening.
Okay.
Think about predicting the weather.
Uh-huh.
The chance of rain might change significantly depending on whether or not there are clouds in the sky.
So that extra information, the presence of clouds, changes the probability of rain.
Exactly.
That's conditional probability.
Exactly. And it's written as P of X given Y.
Okay.
Meaning the probability of X happening given that Y has already happened.
The notes then move on to independent variables.
Okay.
Does that mean events that have nothing to do with each other?
Exactly. Like whether you ate cereal for breakfast probably has no impact on whether your favorite sports team wins tonight.
Yeah.
Those are independent events.
So in that case, knowing one event happened wouldn't change the probability of the other event happening.
Exactly. And the notes point out that the IID assumption, independent and identically distributed, is commonly used in data science.
The IID assumption basically assumes data points are independent of each other.
Right.
And come from the same underlying pattern, right?
Right. Like if we were analyzing blood pressure data, we might assume each reading is independent of the others and that they all come from the same overall distribution of blood pressures in a population.
It seems like a pretty big assumption to make.
It can be, and that's something to be aware of.
Yeah.
Real-world data often doesn't perfectly fit the IID assumption.
Right.
Things like social media trends, where people influence each other, clearly violate that independence rule.
So data scientists need to be careful about when they apply that assumption.
Absolutely.
Now, building on conditional probability, the lecture notes introduce Bayes' rule. I've heard of it, but honestly, it always seemed a bit mysterious.
Bayes' rule is a fundamental concept, and it might seem intimidating at first glance.
Yeah.
But the idea behind it is actually quite simple.
Okay.
It's all about updating your beliefs based on new evidence.
So like having a prior belief about something, then getting new information, and using Bayes' rule to adjust that belief to form a new, updated belief.
Exactly. It's a powerful tool for making inferences and predictions.
Okay.
And as Professor Wu points out, it's the foundation for many machine learning models.
Speaking of machine learning, let's talk about how we actually visualize these probability distributions.
Okay.
I see the lecture notes focus on histograms.
Visualizations are key.
Yeah.
A histogram gives you a visual snapshot of a probability distribution.
Okay.
It takes your data and groups the values into ranges, then uses bars to show you how many data points fall into each range.
So it's a way to see the shape of your data and where the most common values are.
Exactly. Histograms are great for getting a quick visual understanding of the distribution of your data.
And the lecture notes include some Python code examples for creating them. Looks like Python can handle both discrete data and continuous data for histograms.
Right. Python's data visualization libraries make it easy to generate histograms and explore data in a really intuitive way.
Now, the lecture notes delve into a specific distribution, the Gaussian distribution, or bell curve, as it's often called. Why is this one so important?
The Gaussian distribution is everywhere. It turns out that tons of natural phenomena, from people's heights and weights to IQ scores and even errors in measurements, tend to follow this bell-shaped curve.
Professor Wu gives the example of SAT scores being modeled as a Gaussian distribution.
Right.
So if you took a large enough sample of students, their scores would form that bell curve shape.
Precisely.
And a key feature of the Gaussian distribution is that most data points are clustered around the average, with fewer and fewer points as you move further away from the center. But how do you actually use the Gaussian distribution to figure out probabilities?
Sure.
I vaguely remember something about areas under the curve and integrals.
You're remembering correctly.
Oh.
Calculating probabilities with the Gaussian distribution involves finding the area under the curve between certain points. And yes, that involves integration. But thankfully with Python, we don't have to do those calculations by hand anymore.
So Python has functions that take care of those calculations for us.
Yes. Python has made working with probability distributions much easier.
Okay.
It's a lifesaver for data scientists.
Now I see the notes mention the inverse CDF, which sounds kind of like working backward.
It is.
Okay.
Imagine, the probability you're looking for, and you want to find the corresponding value on the Gaussian distribution.
Right.
That's where the inverse CDF comes in.
So instead of saying, what's the probability of getting a specific SAT score, You could ask, what score do I need to be in the top 10%?
Exactly. You're essentially finding the value that corresponds to a certain area under the curve, which represents the probability you're interested in.
And of course, Python has a function for that too, right?
It does. Python statistical libraries are incredibly comprehensive,
Yeah.
making it much easier to work with different probability distributions and calculate all sorts of probabilities. It's like having a powerful toolbox for data analysis.
It's amazing how these probability concepts are the foundation for so much in data science.
It really is. This lecture gave us a great overview of the core ideas.
Yeah.
It's fascinating how these seemingly simple concepts like probability distributions can have such a huge impact on how we understand and analyze data.
Absolutely. And as we've been talking about, Python makes it much easier to actually work with these concepts.
Oh, for sure. Can you imagine trying to do all of this by hand?
Oh my goodness, no.
Python's statistical libraries are a game changer.
Totally. And it's so flexible.
Right.
You can use it to work with all sorts of different probability distributions.
Yeah.
Not just the Gaussian.
That's right. Real-world data rarely fits neatly into a perfect bell curve.
Yeah.
Being able to choose the right distribution for your data is essential.
And even though Python does the heavy lifting for us, it's still important to understand what's happening behind the scenes.
Right.
The concepts of probability distributions and how they work.
Yeah.
Visualizing those concepts, like with histograms, really helps to make it all click.
Definitely. Visualizations help bring those abstract concepts to life and make it easier to see patterns in your data.
This deep dive has definitely given me a lot to think about, and I'm feeling a lot more confident about tackling probability in my data science work.
That's great to hear. Probability is a powerful tool, and now you have a solid understanding of the fundamentals.
Thanks for joining me on this deep dive. It's been a real pleasure.
It's been my pleasure too.